Thank you for checking out our work. My name is Alexander Kim. I'm a master's student at the Technical University of Munich, and I'm happy to present to you our work, EagerMOT, 3D multi-object tracking via sensor fusion. This work was done with the help of my advisors, Dr. Alyosha Osep and Professor Laura Liatache. Multi-object tracking is a task with very many applications, and it's usually done in either of the two modalities, in 3D using LiDAR or stereo, or in 2D using RGB cameras. While the 2D MOT variants are more popular, mostly due to image data being more accessible, a lot more annotations being available, and overall more being known about how to handle image data, 3D multi-object tracking has been a lot more popular in recent years because applications such as urban driving or mobile robotics gained popularity over the years, where precise 3D information that is provided by sensors such as LiDAR is more important. The sensors themselves and the modalities have very easily observed complementary properties. For instance, sensors such as LiDAR are usually sparse and noisy, while cameras provide a very rich signal at each pixel. Cameras also have a very long range, while LiDAR and stereo setups have a limited range of maybe 60 meters or so. LiDARs are also very sensitive to reflectivity, and cameras, while also sensitive, can be trained for longer because they have a lot more available data and also require much less compute. On the other hand, cameras do not provide any 3D information, and LiDAR provides 3D localization information right away, which is crucial for many robotic applications. In our work, we observed these complementary properties, and we work to find a simple yet effective way to combine them to arrive at a superior tracker, which is what we'll be presenting for you today. The final framework that we'll be presenting is experimentally verified to generalize to multiple multi-object tracking tasks, to different object detectors, to hardware configurations, and even sensor capture rates. We proved this with our state-of-the-art results on the KITTI dataset for 3D and 2D multi-object tracking, as well as 2D multi-object tracking and segmentation. On KITTI, we run at 90 frames per second if we exclude detection time. And on the NuScenes dataset, we also submitted our framework to the MOT benchmark, where we are also holding the top place among reviewed and published results. This is the overview of our network, and if you take a closer look, then everything that's not related to 2D, so if we remove 2D detector, fusion, and second data association, the rest is a quite standard 3D multi-object tracking wireframe, and this is very much by design. We wanted to come up with a very simple addition to existing work, build up on existing research, and show that a simple way of integrating 2D information can bring significant improvements. So let's take a look at each module one by one. First is sensor fusion. How do we actually combine complementary sensor observations? In the fusion module, we do this in a very straightforward way. We bring everything to 2D space to operate in the same domain. 2D detections, of course, stay exactly the same, while 3D boxes are projected into 2D and then approximated with a 2D box that's constructed by simply using the outermost edges of the projection. And in the end, you have two sets of 2D boxes which can be matched, and hopefully objects are visible in both sensors, and then their observations will be linked together. In the fusion module, we do this using IOU, intersection over union, a quite standard metric for matching two boxes, and it works out quite well even in our case. In the very end, you will have a set of the so-called fused instances, some of which will include information from both 3D and 2D sensors, so objects such as this car, which was observed in both sensors, and some will have information only from 3D, and some will have information only from 2D, depending on which sensor saw them and which one didn't. Next, after fusion, we will need to talk about matching. And before this, we'll talk about how we parameterize instances and tracks in 3D and 2D space simultaneously. Diffuse instances have the same parameterization as the object detections. In 2D, we simply have 4 values for the bounding box, and in 3D, we have 6 values for the bounding box, 3 location values and 3 dimension values, as well as a single value for the orientation of the box around the vertical axis, so rotation along the ground plane. For each track that we will keep internally in our framework, we have exactly the same parameterization, plus we have a linear common filter acting as a motion model for the 3D state of our track, and it behaves exactly the same way as it is described in the recent baseline paper, a baseline for 3D multi-object tracking published by Wang et al., lastly appearing in ECCV workshop. Please check out this paper for more details on how the track is parameterized and how the common filter is integrated into it. The first association stage is very similar to what is described in the baseline paper. Again, this was very much by design. We wanted to build up on their work and show that simple additions such as integration of 2D information can drastically improve performance. The major difference we made to the first data association stage here is using a different metric. In the baseline paper, the metric they used is IOU. They measured overlap between 2 3D bounding boxes and used that as a metric to judge whether a track belongs to this new observation. In our work, we wanted to have a more lenient, less strict metric because our framework's goal was to keep tracks for longer than for as long as possible to allow them to recover through either 3D or 2D observations. And as such, we expected much noisier predictions. We expected our predictions to be much further from new incoming 3D observations, and we couldn't rely on a metric that was built on overlap. So in our case, we used a simple Euclidean distance between box parameters and scaled it by the cosine of the angle between orientations. Essentially what this does is it measures how similar the two boxes are in location as well as in size, and it also scales it by how similar the orientations of the boxes is. Please check out the paper for more details if you're interested. But this metric is quite similar. It is a heuristic, and its main value was to be more lenient than the overlap metric used in other works. Then we come to the main ingredient of our framework is the second data association stage. Here we take all the unmatched tracks from the first stage, so tracks that would normally be considered unmatched and possibly terminated in other works. We use them in our second stage where we try to match them to instances that were detected only in 2D. So for instance, if a car is occluded and the LiDAR can no longer pick it up, but the camera can still recognize it because it sees a corner of the car behind another car's mirror or something like this, we still have a chance for this track to be kept alive and to be matched to an existing instance. Here we do this using overlap, again similar to the fusion module. We predicted 3D bounding boxes for each unmatched track, projected into 2D space, approximated with a box, and then using IOU as our metric, we match it to existing, to new 2D observations. This gives the tracks an extra chance to be matched to incoming observations, and also gives it a chance to stay alive and avoid termination due to not being matched in the previous stage. Including 2D information allows us not only to recover occluded objects, but also objects that are too far away and can no longer be picked up by LiDAR, or objects that are colored with paint that's very bad for LiDAR. For instance, some shades of black are very hard for LiDAR to pick up, and the second stage association allows these objects to be matched because it works with only partial observation. So if you only have observation from your 2D sensor, you can still keep your track alive and not be surprised when the car comes into 3D sensor range again at the next frame. However, the downside of this approach is that if we do not match a track in the first stage, we no longer have up-to-date information about its position. and therefore our estimates of its future state also get more uncertain. But we assume that it will be able to recover in later frames through this two-stage process once again, because we're using a more lenient matching metric in the first stage. We're using a distance metric, not an overlap metric, which is more robust to noise and to uncertain predictions. Finally, after both association stages are done, we enter a very standard check lifecycle module, which does state updates. So 3D and 2D observations are integrated. 2D information is simply overwritten. 3D information is used to update the common filter motion module. New tracks are created from unmatched instances to account for actors that come into the scene, for new actors that come into the scene. And some tracks are eliminated if they have been unmatched for the last k-frames. All of these rules are quite similar to other state-of-the-art works. The difference is that due to the presence of a second stage data association, some tracks are kept alive longer, some tracks are not eliminated unnecessarily, and are able to recover from longer occlusions, because we rely not on a single sensor but on a set of two. Here's a look at our framework once again. The new additions of our framework are these bottom 2D focused parts, and if you remove them, you will see a wireframe for any recent 3D multi-object tracking method. The experiments we did to show that using 2D information is beneficial is presented in the next slides. For instance, here we show the results on the NuScenes dataset, where we compare to other works that have been submitted to this benchmark. We show results that are much higher than any of the published work, and also higher than any of the work that's been concurrently done, but not yet peer-reviewed. We also did extensive evaluations on KITTI. We compared on the validation set our 3D mod performance. We followed the same protocol as the baseline paper. We also brought our framework to the same parameters as the baseline paper. We used the same 3D detections, and we showed that simply because we have this 2D sensor fusion logic, we are able to get results that are much higher than the baseline. We also submitted our framework to the 2D mod benchmark, where we show that even though we're tracking objects mainly in 3D, if we project them into camera space, we obtain state-of-the-art results, even on the test set, which is more reliable than the previously shown validation set evaluations. Lastly, we also showed that our method generalizes to the MOTS task, which is tracking plus segmentation, where we took segmentation masks that were produced by another method, MOTS fusion, and we showed that if we use our tracking formulation instead of theirs, we achieve much better results in much higher frame rate. Please check out the paper for details on this evaluation. Once again, this is the wireframe. Hopefully it's more understandable for you now that we've looked at everything. The main additions are the second data association and the fusion. Fusion is quite straightforward, as is second data association, and any improvements to metrics and to the logic is a subject of future work. And this paper was mostly a proof of concept that using complementary sensor sets will provide benefits when evaluating tracking performance. Thank you for listening. Please check our paper for details, for instance, how we handle multiple cameras in the NuScenes dataset, and also on our detailed ablation studies to see that our additions actually do provide value. If you have any questions, please open issues or send emails, and we hope our work was useful to you. Thank you.